Has this ever happened to you?
Oh man!
Owie, ouch, ow. I have an headache. Age? I don't know how old I am. Oh no, my phone is about to die. If only my shirt could charge it. I am so ready for this fresh new beverage. Glug glug glug. Oh no, not again. If you could relate to any of those situations, then maybe carbon nanotube for you. It is the only material that can do actually anything. What not to love about that? Buy today, or in 20 years. Only $9.99. 99. 99. 99. 99. 99. Really? But what do Carson's Nana's shoes have to do with me overdosing on Tylenol 20 seconds ago? Well, you see, kid. Kid? We're the same age, like the exact same age. We are the same person. A carbon nanotube is the equivalent of a sheet of graphene, hexagonally bonded carbon, rolled up. That means absolutely nothing to me. Same. Due to the nature of the bonding of these nanotubes, the possibilities for commercial use are almost endless. That's why we here at Kuckmokin, corporation of a Chem monopolizing manufacture of carbon nanotubes, have put a patent on any and all carbon nanotube products. I'm still lost. Let's get into the science of it, shall we? Well, go on then. What? No, are you crazy? I'm not explaining them to you. They just pay me to be in these infomercials, not to understand any of the bullcrap I'm saying. They pay you? In the simplest manner, as said previously, carbon nanotubes can be imagined as sheets of graphene, imagine this was flat, but I tried my best, rolled up into tubes. Since each carbon atom only has 3 single bonds, this means that delocalized pi bonds will form on the outside and inside of the nanotube, making it extremely conductive. Most manufacturing processes to create carbon nanotubes do not actually form single-walled nanotubes as you see here. They form multi-walled nanotubes. These can have any number of layers, more than one of course, that's the multi. The easiest to manufacture have upwards of 20. When created, carbon nanotubes can be turned into either a plastic-like material or spun into thread.
I told you that carbon nanotubes are not synthesized as a graphite sheet that rolls up, so how are they made? The mechanism is still not fully understood, but in this video I will show you the setup for the main different techniques used by scientists to produce carbon nanotubes. There are 2 main techniques. The first one to be used was arc discharge. This is the chamber for the arc discharge, which is filled with an unreactive gas. Inside, 2 rods of graphite will be placed and we will apply a current. One of the rods will be the anode and the other will be the cathode. When the 2 rods are brought together and the current is applied, a spark is produced between the rods, which instantly vaporizes the tip of one of the rods, and this carbon gas forms the nanotubes. Black soot is produced and starts to cover the whole chamber, including the window, so after a while we can't see anything anymore. When we open the chamber, we can see how the anode is being consumed, and the black powder is deposited everywhere around. On the cathode there is also black powder, where we will find carbon nanotubes, normally with 20 to 30 walls, although if we also include a metal catalyst in the anode, we can obtain single-walled nanotubes. The nanotubes made with this technique are quite perfect, free of defects, but the problem is that there are another bunch of carbon forms that are also produced, so then it is very difficult to separate them. It's also hard to make a lot this way. The other main technique is chemical vapor deposition, but it is most commonly known by its abbreviation CVD. In this case, the starting material is not graphite, but some carbon-based gas, a hydrocarbon. We also need a metal catalyst to form tiny particles which will act like seeds. In this CVD machine at Oxford University, the metal is included in the starting molecules. They use ferrocene, which contains 1 iron atom per molecule. The young scientist takes a clean tube and sets up the experiment. He introduces a clean base in the tube and closes all empty space with heat-resistant cotton to keep the heating. A non-reactive gas is passed through the heated solution of the hydrocarbon. The mixture passes through the furnace where the temperature can be from 300 up to 1150 degrees C. He can run the experiment for as little as 5 minutes up to hours in order to get longer tubes. Once the experiment is finished, he collects nanotubes from the soot stuck on the tube sides. and also the base, previously clean, which now has nanotubes all over it. CVD is probably the most promising method to produce carbon nanotubes for industrial use. It is easy to introduce other elements such as boron or nitrogen in the starting chemical. The diameter of the tubes can be chosen by the size of the metal catalyst particles. Also, we can grow the tubes on the surface, which helps for future applications. Arc discharge and CVD are the most common techniques, but there are others, like laser ablation. In this technique, a laser is used to vaporize the carbon atoms from a graphite target. Laser ablation normally produces single-walled nanotubes. Another less common technique is electrolysis. This technique is in some ways similar to the arc discharge, because it also uses two graphite electrodes. But in this case, the electrodes are immersed in molten ionic salts. With this technique, only multi-walled nanotubes are produced. They have very few walls, 10 to 15, and are normally bundled together.
There are actually hundreds of ways to produce carbon nanotubes, most of them theoretical, but many of them are being put into use around the world. That was a very nice episode of how it's made and all, but pants are expensive. How are carbon nanotubes going to help me stop the bullies from tearing them off every day? Now to the disembodied voice haunting my computer for more on that topic. Medicine. Carbon nanotubes can actually be filled with medicine or other such medicinal treatments that need to be carried throughout the body. Since they are in fact nano-sized, about 10,000 times thinner than a human hair, the amounts can be extremely precise. When near-exact amounts of medicine are used when treating certain diseases, things like toxicity and other side effects are reduced, while things like efficacy are improved. Thermoplastics. Scientists are always looking for new kinds of safe, versatile materials, and carbon nanotubes fit this to a T. Carbon nanotubes can be combined with various resins and thermoplastics to form extremely durable products, such as water bottles, Tupperware, phone cases, car bumpers, and can even be used in spacecraft. Cloth. The tube shape of carbon nanotubes, combined with the intermolecular forces between different tubes, allows for them to be pulled into a thread.
These aren't just ordinary carbon nanotube forests. They are nanotube forests that have a very special type of connectivity between nanotubes. When we pull out one nanotube, that nanotube pulls out its neighbors, who pulls out other neighbors to self-assemble a yarn or a sheet.
A second, more recent method has also been presented.
So we have carbon nanotubes that are dissolved in a solvent, which is chlorosulfonic acid. And this solution is a very viscous type of material, so it's kind of like mayonnaise almost in viscosity. And we're extruding it through 19 small holes and then winding it onto a drum.
These threads can be spun into cloth and be used to make things like clothing, sails, bridge cables, and even armor stronger than Kevlar. Because of the conductive nature of carbon nanotubes, all of these materials can be conductive as well, if needed. Otherwise, they can be coated in nanoinsulators for purposes such as safety. Electrical. Conductivity and durability of carbon nanotubes opens up infinite possibilities in the electrical field.
So what you're looking at here is two bundles of our nanotube fiber that are holding up an LED light bulb that weighs 50 grams. Those fibers are also being used to run the current that's powering the bulb. So this is demonstrating the multifunctionality of the fibers, that they are strong enough to support the weight of the bulb and also have high enough conductivity to provide the current.
Since there is also a such thing as multi-walled carbon nanotubes, current could pass through a single multi-walled nanotube in multiple directions. Since they are so small, carbon nanotubes also open up endless opportunities for computer engineering, possibly allowing for nanocomputers to be created. Their size also allows them to be almost completely transparent when pressed between sheets of plexiglass. This could allow for more efficient windshield or window insulation, or even highly improved solar panels. If executed correctly, future scientists could create carbon nanotube clothing with carbon nanotube solar panels on it, meaning you could charge your phone through your pants pocket from lounging in the sun. So if I'm understanding this correctly, carbon nanotubes are freaking amazing because of their versatility, conductivity, durability, and continuity? I'm not sure if that last one is correct. But basically, yeah. Sweet! Then I'd like to order one pair of those medicine-delivering, phone-charging, pasta-holding pants, please. Okay, we'll have them delivered to you within 20 to 50 business years, maybe. And that'll be $12 million. Awesome!